Okay, we now talk about the areas between curves. We have seen why the formula is true using infinitesimal method. Now let's recall the setup. The plane region here is enclosed by two curves and two vertical lines. The top curve, we call it top boundary. The top boundary is the graph of function f of x. The bottom boundary is the graph of the function g of x. Both functions are defined on the interval from a to b. We are going to call a region like this the region with a top boundary and a bottom boundary over the interval from a to b. If all the conditions are true, including this condition, it means the graph of f of x is above the graph of g of x. Right? If all the conditions are true, then we can use that formula to compute the area between the two curves over the interval. Now we are going to use a few questions to illustrate how to use the formula to compute the areas. Okay. Now look at question 1. In question 1, the plane region is enclosed by two curves and two vertical lines. The setup is exactly the same as the setup in the conclusion. Actually, one curve and three lines. This is the graph of a line. In any case, the first thing we do is to sketch the plane region. Now I'll show you the solution. Okay. The first thing we do is to draw a sketch. By that we mean we draw a sketch of the plane region. On rectangular coordinate system, we know the graph of e to the power of x, right? Now let's say that's point 1 on y-axis. The graph of e to the power of x is in that shape. This is the graph of that function is a straight line. We all know the shape of that graph. The graph of y equals x is a straight line, so something like this. And correspondingly, there are two vertical lines. One vertical line has the equation x equals 0, and the other vertical line has the equation of x equals 1. The vertical line x equals 0 is y-axis, right? We want to call the horizontal axis x-axis, and that's y-axis. Again, x equals 0 is y-axis, and the vertical line x equals 1 is a vertical line, something like this. Now let's say this point is the point on x-axis with the coordinate of 1. So the plane region is enclosed by two curves and two vertical lines. This vertical line, the second vertical line, is something like this. So the plane region for which we are going to compute the area is the shaded plane region. Okay. In any case, in step 1, we draw a rough sketch, so that you see what's going on. Strictly speaking, you need to verify the curve for the exponential function is above the line, but it's kind of obvious in this case, right? Okay, now the plane region can be treated as a region with a top boundary, the graph of e to the power of x, and a bottom boundary, so which is the graph of y equals x. I'm going to label the graphs, the curves using the function, using the equation of the graph. Okay, this one is the graph of y equals e to the power of x. This line has the equation y equals x. The second step, now look at the formula. Okay, the second step we need to do is to get the interval on which we need to compute the integral. We need to figure out the interval AB. Okay. If the region is treated as a region with a top boundary and a bottom boundary, then we can project the region onto the horizontal axis so that we can get the interval. I will write something down. We project the plane region onto x-axis. We get the closed interval from 0 to 1. From 0 to 1. This is the interval on which we are going to do the integral. Now, thirdly, we need to treat the region as a region with a top boundary and a bottom boundary. And then we need to identify the function representing the top boundary and the bottom boundary. We'll make the notations consistent with the notations in the statement of the conclusion. By that we mean we are going to use f of x to denote the top boundary. We are going to use g of x to represent the bottom boundary. The third step, we try to give a description of the region. Okay. Now the region, the plane region, for which we are going to compute the area, can be viewed as a region with the top boundary. The notation in the statement, the top boundary is represented, is supposed to be the graph of f of x. I'm going to use the notation f of x for the function representing the top boundary. Okay. The top boundary, now let's say f of x equals, now look at the region. The top boundary is the graph of y equals e to the power of x. So in this case, f of x is equal to e to the power of x. With the top boundary of that and the bottom boundary. I'm going to use g of x to represent the bottom boundary. So basically the bottom boundary is supposed to be the graph of g of x. Look at the region again. The bottom boundary is the graph of y equals x. So g of x in this case is x. Over the interval from 0 to 1. Now let's see the whole thing, okay, in step 3. Now the plane region can be viewed as a plane region with the top boundary. You have the top boundary is the graph of f of x, which is e to the power of x. And the bottom boundary is the graph of g of x equals x. You also need to identify the interval, okay. Now we have all the information we need in the formula. We got the interval, we got the function representing the top boundary, we also have the function representing the bottom boundary. Now we are ready to use the integral to compute the area, okay. So the area of the plane region, we use A to denote the area of the plane region, is computed using the integral from 0 to 1 in this particular case. The interval, we got the interval from step 2. And then the function representing the top curve is e to the power of x. Can still use the notations f of x and g of x in here. So just try to see what we need in the formula, okay. In the formula, f of x is the function representing the top boundary. We just copy the formula. And then we plug in the functions. And that's the idea, okay. Minus g of x. G of x is the function representing the bottom boundary, dx. We plug in the functions from 0 to 1. F of x in this case is e to the power of x. And the g of x in this case is x, right? The integral is easy to compute. Maybe we'll move on to compute the integral. Okay. To get the integral, you get a particular antiderivative of the integrand. So which is e to the power of x. Antiderivative of e to the power of x is e to the power of x. And the antiderivative of x is half of x squared. And then we use a notation like that. So because the antiderivative is a little bit long, we're going to enclose the antiderivative in square brackets. And then this notation means we compute the difference between two values of the antiderivative. By that we mean we plug 1 into the antiderivative, we plug 0 into the antiderivative, and then we get the difference between the two values of the antiderivative, right? So it's we plug 1 in, you have e to the power of 1, we just write e, okay? And then you plug 1 into that function. I think you have minus 1/2. That's the value of the antiderivative at 1. And then we minus the value of the antiderivative at 0. E to the power of 0 is equal to 1, right? E to the power of 0 is equal to 1. X squared over 2 at 0 is equal to 0. We just need to subtract e to the power of 0, so which is 1. Finally, the answer I believe we are going to get e to the e minus 1/2 minus 1, you have 3/2. That's the area of the weird region. Later on, we're going to do a few more questions regarding how to use the formula. But now let me summarize a little bit. The first thing we do is to draw a sketch. By that we mean you try to sketch the plane region. The second thing we do is to project the plane region onto one of the axes, either x-axis or y-axis. Okay. Our target is to get a closed interval. This is the interval on which we need to compute the integral so that we can get the area. Okay. And then if the region, the plane region, can be treated as a plane region with a top boundary and a bottom boundary over some interval. So maybe you try to give a description so that it's easier to see what's going on. Identify the top boundary, identify the bottom boundary, identify the interval. After we get everything we need, we plug everything into the formula, and then we can have the area, right? Evaluate the integral, we can have the area. Okay. We'll work on one more question in that nature. Now look at the question. We'll follow the step procedures we mentioned in question 1 to get the area of the region enclosed by two parabolas. Okay, now the solution. It's easy to graph this parabola, y equals x squared. That's a parabola. All of you guys know how to sketch that. And then to get the sketch of the second parabola, if we do not use a graphing calculator, we need to complete square. I will show that. The function, the second curve, the second parabola, you know that's a quadratic function. The graph of any quadratic function is a parabola, right? To sketch the graph, we complete square. So y equals 2x minus x squared. By completing square, we mean to rewrite the function in that form. I'm going to use that later. In the form of y equals some number a times x plus or minus a number b, the whole thing squared, and plus or minus a number c. That's our target. If we can rewrite the function in that form, then we are done completing square. Okay. We learned this in high school. The first thing we do is to rewrite the function in this form. Now let's say negative x squared minus 2x. And then in here we're going to add a number to make the first three terms a perfect square. The number we need to add in here is always half of the coefficient of x, the whole thing squared. The coefficient of x is negative 2. Half of negative 2 is negative 1. Negative 1, the whole thing squared, is 1. So we add 1 in here. You are going to see in next step the underlined three terms are going to be a perfect square as x minus 1, the whole thing squared. I will show you later. Okay. In order the equation is valid, we add 1, we have to minus 1, so the equation is valid. We'll keep on going in here. Now, all of you guys know the underlined three terms is a perfect square as x minus 1, the whole thing squared. Okay. We still keep the negative sign. We'll put everything else in square brackets. Again, the underlined three terms will become x minus 1, the whole thing squared. You still have to copy the negative 1 in here, right? Eventually, you'll have negative x minus 1, the whole thing squared, and then plus 1. That's what we meant by completing square. Now look at the final form. This form is, in that form, a number -1 times x minus 1, the whole thing squared, plus or minus, in this case, plus 1. That's how we complete square. Why do we complete square? It's because we want the graph of the function. We want the graph of this function. Look at the mouse cursor. To get the graph of the function, we start from the graph of y equals x squared. So something like that. Illustration only. And then we do some shifting and stretching and stuff to make the graph of the required function, so which is the same thing as the complete squared form. We start from the graph of y equals x squared, and then probably we're going to get the graph of, so now let's say y equals negative x squared. We're going to make the negative sign in this final form. That's the second step. From the graph in step 1, now let's recall what we learned in high school. We reflect the graph in step 1 by the horizontal axis. Then we can have the graph of y equals negative x squared. Something like that. That's step 2. And then in step 3, we replace x with x minus 1. So by that we mean we're trying to get the graph of y equals, let's say, negative x minus 1, the whole thing squared. From step 2 to step 3, we replace x with x minus 1. Now let's recall what we do. We shift the graph in step 2. If you see minus 1 here, we shift the graph in step 2 to the right by 1 unit. That's how we do it. Now let's say 1 is here, the origin is here. In step 3 we have a graph, something like that. Finally, we can get the graph of the required function in step 4. In step 4, we just need to add 1 to the function in step 3. Right. I will squeeze the graph in here. Okay. Now in step 4, we are going to get the graph of the required function, so which is the graph of y equals, let's say, negative x minus 1, the whole thing squared, and then plus 1 from step 3. From the function in step 3, you add 1, you get the graph of the function in step 4. or the required function, right? If you add 1 in here, it means we shift the graph in step 3 up by 1 unit. So eventually you have a graph something like this. The vertex in here is 1, 1. The parabola is facing down. I was trying to tell you how to sketch the graph of the second parabola without using a graphing calculator. Okay. I will leave that on the screen. Okay, now we draw the first step. The first thing we do is to draw a sketch. The graph of the first function y equals x squared. All of you guys know that. I'm going to use the dotted line to denote the part which is not in the region. This part is going to be in the region, right? That's the graph of y equals x squared. Earlier we have seen how to get the graph of 2x minus x squared by completing square. Now let's recall the graph of 2x minus squared, y equals 2x minus x squared. It's something like this. The whole function is something like that. I'll try to make the graph a little better. Illustration only again. Okay. So the shaded region is the region enclosed by two parabolas. And one additional question. So some people also might think why the origin is on this parabola. So because 0, 0 satisfies the equation, you plug x value of 0 in and y value is equal to 0. That means the origin is on that parabola, right? So the origin is on the curve. Okay. Now we're done the sketch. In general, in the second step, we want to get the interval on which we need to evaluate the integral. It's the same thing. We project the region, the plane region, onto the horizontal axis to get an interval. But at this point, to project the solid onto the horizontal axis, we need this point. We need the coordinates of this point. In general, if you have some points of intersection, you need to solve a system to get the points of intersection. We're going to add one more step. In this particular case, it's easier to guess the point of intersection. But in general, we need to solve a system. I will add one additional step showing you how to get points of intersection. Okay. We solve a system. the system with the two equations and the two variables. Y equals x squared. That's an equation giving you the bottom boundary. And the top boundary is y equals 2x minus x squared. Okay. Maybe I'm going to label the boundaries using the equations. The top boundary is the graph of y equals 2x minus x squared, and the bottom boundary is the graph of y equals x squared. Okay, to solve the system, I'm going to call this equation 1. This one is equation 2. You can use any method you learned in high school. Now let's recall we learned two ways in high school. One way is called the substitution. The other way is elimination. Either way is okay. Okay. We plug 1. So basically we plug y equals x squared into the equation in the second equation. Our target is to eliminate one of the variables. By that we mean we can eliminate y in this particular case. Okay. I will write some more details. We plug 1 into 2. Our target is to eliminate y. Okay. Wherever you see y, you replace y with x squared. So you have x squared equals 2x minus x squared. So we have a quadratic equation of x. This equation is equivalent to 2x squared minus 2x equals 0. And then you cancel out 2. For when solving an equation, it's permissible to multiply two sides of the equation by a non-zero number, or divide two sides of the equation by a non-zero number. We divide the equation by 2. We have x squared minus x equals 0. To solve a quadratic equation, we factor the equation. The factored form is x times x minus 1 is equal to 0. Using the factored form, we can get the solution to the equation. Right? The quadratic equation has two solutions. One equation is x equals 0. The other solution is x equals 1. In many cases, you do not need to get the actual points of intersection. All we need is to get x coordinates of the points of intersection in this particular case. So, but still, it's easy to get the points. Okay. We plug these two numbers into one of the two equations in the system. Correspondingly, we have y value equals 0. You plug x value of 0 into y equals x squared. So you see y is 0 squared for the x value of 0. So y value is 0. Okay. And also you have when x value is 1, you have y value equals 1. Okay, put the solutions that way. Now for the system, the system has two solutions. One solution is x value of 0 and y value is 0. The other solution is x value is 1 and y value is 1. Okay. Each solution will determine a point of intersection. Now we have the points of intersection. The 2 points are 0, 0 and 1, 1. Again, for this particular question, it's easy to guess the points of intersection, but I was talking about, I'm trying to use this question to illustrate something in general. The second step in many cases is to get the point of intersection. At least you get x coordinates of the point of intersection. I'm going to label the points of intersection. This point is of course the point 1, 1. This point is the origin, the point 0, 0. After getting the points of intersection, after getting the coordinates of the points of intersection, then we can easily get the interval. Now in step 3, we are trying to get the interval. In step 3, now let's recall how we get the interval. To get the interval, we project the plane region onto x-axis. We get the interval. The interval is, after getting the points of intersection, we know the interval. You project the solid onto, you project the plane region onto horizontal axis. We know the interval is the interval from 0 to 1. We get the interval from 0 to 1. This is the interval on which we need to evaluate the integral to get the area of the region. I will complete the solution soon, but now I want you to see. Now this region can be viewed as a region with a top boundary and a bottom boundary. We know the equation representing the top boundary. We know the function representing the top boundary. We also know the function representing the bottom boundary, so that we can use the formula. I'm going to complete the solution by writing something down on the next slide. Now step 4. The plane region now can be viewed as a region with a top boundary. We identify the top boundary first. I'm going to use f of x to denote the function representing the top boundary. The top boundary is the graph of the function 2x minus x squared. And the bottom boundary. Okay. The bottom boundary is also a function of x. I'm going to use g of x to denote the function representing the bottom boundary, to make the notations consistent with the notations in the conclusion. the bottom boundary is the graph of the function x squared, y equals x squared. I'm going to use g of x to denote the function representing the bottom boundary over the interval from 0 to 1. Now we have everything we need to set up the integral. So the area is the area of the plane region enclosed by two parabolas. The area of the shaded region. The interval is from 0 to 1. I still use the notations f of x and g of x to make everything consistent with the formula. And then we plug in functions from 0 to 1. F of x, I believe it is here. F of x is 2x minus x squared. And the g of x is x squared. I will do one more step. From 0 to 1, the integral now is 2x minus 2x squared. It's super easy to evaluate the integral because the integrand is essentially a polynomial. I'm not going to evaluate the integral. Okay, we only set up the integral. That's the second question we want to go over. And by the way, for question 2, this plane region can also be viewed as a region with left and right boundaries. In which case we need to use the formula in item number 2 in that item. Now I want to make some comments on the second formula. In some cases, it's easier to view a region as a region with left boundary and a right boundary. In which case, the right boundary is the graph of a function in the form of x equals f of y. So here you treat x as a function of y. And likewise, there's another curve. This curve is the graph of the function x equals g of y. These two functions are both defined over the interval from c to d. Of course, the interval from c to d is for y values. The two curves defined on the interval from c to d, together with two horizontal lines, y equals c and y equals d, they form a plane region. I know in high school we did not learn any functions like these. We treat x as a function of y. But I think it's not too hard if you imagine we switch x and y. So the graph of a function when x is a function of y should be something like that. If all the conditions are satisfied, I want you to see the condition f of y is greater than or equal to g of y for every y on the interval. This means the graph of x equals f of y is to the right of the graph of x equals g of y. If all the conditions are satisfied, then we can use that formula to evaluate the area of the plane region with the left and the right boundaries over the interval when y is on the interval from C to D. Now I want to use a particular question to illustrate how to use the second formula. For the question on the screen, the plane region is enclosed by a straight line and a curve. This is a parabola. We'll do a sketch soon. Now the solution. In any case, in step 1, we draw a sketch. On rectangular coordinate plane, the line has the equation y equals x minus 1. Now look at the mouse cursor. The graph of y equals x is something like this, passing through the origin, and then we shift the line downward by 1 unit. We have the graph of y equals x minus 1. Now let's say 1 is here on x-axis, and 1, this point should be on y-axis. This point should be negative 1. X-axis is here, and the y-axis. I will label the line later using a slightly different equation. You are going to see why soon. For the parabola, we did not see any parabola with the equation like this in high school. But I will show you how to get the graph. Starting from the given parabola, y squared equals 2x plus 6. We solve that equation for x. So basically what I want to do is to write x as a function of y, so that we can see the graph. We can identify the shape of the graph. From this equation, we have, let's say 2x equals y squared minus 6. We solve the equation for x. We divide two sides of the equation by 2. We have x equals half of y squared minus 3. If we convert the equation in that form, now we can see the graph of the curve, or the graph of the function. Now we treat x as a function of y. To see the graph of the function, we start from the graph of, now let's say x equals y squared. It's not hard to imagine, or at least you can try to sketch some points, plot some points, and then you connect the points to get the graph. I think it's not hard to imagine the graph x equals y squared. It's a parabola facing right. A parabola facing right. I will move the graph x equals y squared to the far left, so I have enough room. The graph of y x equals y squared, x as a function of y, is a parabola facing right. Something like that. Illustration only. X equals y squared, sorry. I will call that the graph in step 1. From the parabola in step 1, we are going to get the graph of, now let's say x equals half of y squared over 2. In this case, we do a vertical stretch or compress. If you're confused, try to get some particular points so that you can see it's compress or stretch. Now let's say for the graph in step 1, the point with x coordinate of 1 and the y coordinate of 1 is on the curve. So because 1, 1 satisfies the equation, you plug x value of 1 and the y value of 1, the equation is satisfied. For this graph, if you set y value to be 1, then x value should be 1/2. I'm trying to say, for this curve, the point with x coordinate of 1/2 and the y coordinate of 1 is on the curve. This will tell you the shape of the graph. From here, you either do a vertical stretch or compress. So because the point with x coordinate of 1/2 and y coordinate of 1 is on the graph, so the graph, it should be something like this. The point with x coordinate of 1/2 is here, and the y coordinate of 1, now let's say is here. Now let's say x coordinate of 1 is here. Okay, this is the point on the graph. That's the point with x coordinate of 1/2 and y coordinate of 1. So starting from here, this is the point on the graph. You know you are going to do a vertical stretch to get the graph of x equals y squared. The point is here, right? The origin is on the graph. You do a vertical stretch. So that's how you get the graph x equals y squared over 2 from the graph x equals y squared. Illustration only. I know this part is not perfect. And then that is the graph in step 2. The next step is easy to imagine how to get the graph x equals half of y squared minus 3 from the graph in step 2. I believe you can imagine if you shift the graph in step 2 to the left by 3 units, and then you can get the graph of the required function. So lastly, the graph of the required function, the required curve. I will write step number 3 is something like this. You shift the graph in step 2 to the left by 3 units. Now let's say you have negative 3 in here, the origin is here. So the graph of the parabola is kind of in that shape. Now we haven't done draw a sketch yet. We'll move to the next. Yeah, probably we can do it on this screen too. So you have the graph of the line in here, and then the parabola with the equation y squared equals 2x plus 6 is in that shape. Now let's say you have negative 3 in here, and then the parabola is facing right. something like that. Again, illustration only. So the plane region is the region enclosed by the straight line and the parabola. The region is the shaded region. I'm going to shade the region. Okay, now it's something important. You think, is it easier to view the region as a region with upper boundary and the lower boundary, or a region with left and right boundaries? I want to repeat my question. Is it easier to view the region as a region with top and bottom boundaries, or the region with left and right boundaries? Now look at the plane region. The plane region, it is easier to view the plane region as a region with left and right boundaries. You're going to see very shortly. Actually, the left boundary is the parabola. The right boundary is the straight line. In this case, we are trying to use the second formula. When using the second formula, we want to write x as a function of y. Now I'm going to label the boundaries, the left boundary and the right boundary. In the question, the left boundary is the equation of the line. The equation of the line is y equals x minus 1. But when using the second formula, I want to write x as a function of y. The equivalent form is the following. Solve this equation for x. We want to write x as a function of y. I'm going to label the right boundary, the straight line, with the equation x equals y plus 1, which is equivalent to the form given in the question. And likewise, for the left boundary, I'm going to rewrite the equation of the parabola by solving the equation for x. We write x as a function of y. The form is here. The equation of the left boundary, I'm going to label the curve using that equation. X equals half of y squared minus 3. Again, we want to write the equations in those form. So because in the formula, the right boundary is represented as x equals a function of y. X is a function of y, and so is the left boundary. We'll make more comments later. We're done step 1. We did a sketch. In the second step, we get points of intersection, so that it's easier to get the interval on which we need to evaluate the integral. To get the points of intersection, I'm going to write it down. To find points of intersection, we solve a system of equations. The system with the given two equations. One equation is y equals x minus 1. The other equation is y squared equals 2x plus 6. I'll call the first equation equation 1. The second one, equation 2. You can use any method you want, but I'm going to eliminate y by plugging the express in equation 1 into equation 2. Now we plug equation 1 into equation 2. We get the left hand side y squared will become x minus 1 the whole thing squared. Y squared x minus 1 the whole thing squared equals 2x and plus 6. Essentially, that's a quadratic equation of x, but to solve the equation we need to multiply out the left hand side. X minus 1 the whole thing squared is x squared minus 2x and then plus 1 equals, the right hand side is 2x plus 6. Then we move everything to the left hand side. We have x squared minus 4x minus 5 equals 0. To solve a quadratic equation, we need to factor the equation. Using the factors form, we can get the solution to the equation. Factor the left hand side. We have x minus 1 times x plus 5. Sorry, it's wrong. We have x plus 1 times x minus 5 equals 0. Using the factored form, we can solve the equation for x. The equation has two solutions. One solution is x equals -1. The other equation is x equals 5. Now plug x value of -1 into that equation, equation 1. We can get y values. X value -1, we have y value is -2. Right? Correspondingly, we have two solutions to the system. One solution to the system is the solution with x value of -1. Again, you plug -1 into equation 1. You have the y value. Y equals -1 minus 1. So y value is -2. That's one solution to the system. Corresponding to x value of 5, we have another solution. The solution is given by x value is -5, x value is 5, and then you use equation 1 again, you get the y value. You subtract 1 from x value, you have the y value, right? So you have y value equals 4. Correspondingly, we have 2 points of intersection. There are 2 points of intersection. One point is the point with x coordinate of -1, y coordinate of -2. The other point is the point with x coordinate of 5 and the y coordinate of 4. I'm going to label the 2 points on the plane region. This is the point. Now look at the cursor, the mouse cursor. This is the point with x coordinate of -1 and the y coordinate of -2. I'm going to label the point using the coordinates. -1 x coordinate and -2. This is the point with x coordinate of 5 and the y coordinate of 4. We're done step 2. We got points of intersection. After getting the points of intersection, then we can get the interval on which we evaluate the integral. Now we move on to step 3. So please try to remember the graph. We move on to step 3. To get the interval, because the interval is going to be an interval of y, this time we're going to project the plane region onto the vertical axis, onto y-axis. Now look at the sketch, look at the points of intersection. After getting the points of intersection, it's easier to identify the interval. The interval is obtained by projecting the plane region onto the vertical axis. Alternatively, you can just think, what is the smallest possible value of y? What is the largest possible value of y for the points in the plane region? We project the plane region onto vertical axis. I think it's not hard to see. The interval is the interval from -2. That's the y coordinate of this point. That's the y coordinate of this point. To 4, which is the y coordinate of this point. That's how we get the interval. I will write some wording for step 3. We project the plane region onto y-axis. We get the interval from -2 to 4. The closed interval. So we have the interval on which we need to evaluate the integral, the interval we need in the formula. Lastly, the plane region now can be viewed as a region with the left boundary. The left boundary of that. The left boundary has the equation x equals half of y squared minus 3. The right boundary has the equation x equals y plus 1. I will give a description of the plane region before I apply the formula. Okay. Now the plane region can be viewed as a region with the right boundary. The right boundary, in the formula we use f of y to denote the right boundary. By that we mean f of y is y plus 1. Again, to use the second formula, if we treat the region as a region with left and right boundaries, you need to write x as a function of y. The right boundary and the left boundary are represented using a function of y. Now the plane region can be viewed as a region with the right boundary. The right boundary, I'm going to use f of y. The notation is consistent with the notation in the formula. F of y, the right boundary is a function of y. Solve the equation for x, write x as a function of y. F of y is y plus 1. And the left boundary, again, the left boundary should be a function of y if we treat the region as a region with left and right boundaries. In the formula, the notation for the left boundary is g of y. The left boundary, you write x as a function of y. This is a function of y, half of y squared minus 3. So g of y is half of y squared minus 3. I will also specify the interval. The plane region can be viewed as a region with a right boundary and a left boundary over the interval from -2 to 4. I will specify the interval is for the y values. Y on the interval from -2 to 4. It's kind of the summary for all the information we need to set up the integral. We have the function representing the right boundary. We have the function representing the left boundary. We have the interval. Therefore, the area of the plane region A can be evaluated using an integral on the interval from -2 to 4. I'm going to write the basic formula. The function f of y representing the right boundary minus the function g of y representing the left boundary dy. Do not write dx. So because we are doing an integral of y. And then we plug in functions from -2 to 4. F of y is y plus 1. G of y is half of y squared minus 3. dy. The integral is super easy to evaluate. Essentially, the integrand is a polynomial of y. I will stop here.